Hi, welcome to Modern Optimization Methods. Today we will talk about the fourth part of Chapter 4, how we solve the subproblem. We will mainly introduce the dogleg method as well as the two-dimensional subspace minimization. Actually, we have introduced the dogleg method in the previous part. Recall that the dogleg method basically takes two line segments to approximate the optimal trajectory of the subproblem. So we choose the first line segment as PU, this direction, and the second line segment is connecting PU with the full Newton step PB. So with the two line segment, the dogleg method basically solves the following subproblem. We substitute the two-segment path into the model function and we try to find out the one-parameter tau. This will be the dogleg method. And let's first talk about the properties of dogleg method. So we have the two properties about the dogleg method. First is the length of p tilde tau is an increasing function of tau. In other words, as tau increases, the length of p tilde tau will increase as well. So this is a natural common sense from our analysis before. And the second result is that the model function with respect to p tau is a decreasing function about tau. In other words, as tau grows bigger and bigger, the model function will be decreased. Now, to prove the result, let's first take a look at the first part. So for the first part, actually when tau is between 0 and 1, the result is very trivial, so we didn't present this part. We only focused on tau between 1 and 2. To show that the length of p tau is an increasing function, we define an function h alpha as the norm of p tau. Okay, so it is a norm square of p tau. And meanwhile, we do a translation. We replace the tau between 1 and 2 by a function of alpha between 0 and 1, and 1 plus alpha is the original tau. Okay? Now for h alpha, the interval is between 0 and 1. If we do the expansion to h alpha, we can get the following expansion. Okay, so we got a norm about a constant pu, and the linear term about alpha is like this, and you got a quadratic term about alpha with coefficient pb minus pu, the quadratic norm. So to show that h alpha is an increasing function, notice that h alpha is a quadratic function about alpha. So we can take the gradient to show the increasing property. Now let's take the h prime alpha, which is the gradient of alpha. Then we try to prove that it is non-negative. By doing this, we can show the increased property about h. Now let's see whether h prime alpha is non-negative or not. So h prime alpha, if we take gradient, then we can get the constant term and the linear term about alpha. Okay, so by this prime expression, because you got the second term to be non-negative 1, so it is greater than the first term. Okay, so this is a very trivial one. Then next we will substitute our definition for pu and pb to get this equality here. And we rearrange a little bit about this part, then we can get the equality here. So we got some coefficient here and then the red part. Okay, so actually the red part is a non-negative one. then we can see that this is greater than or equal to 0. So overall, we can prove that h prime alpha is non-negative 1. Therefore, the original h alpha is an increasing function about alpha, which then shows that the length of p tilde alpha is an increasing function about alpha. Here, we leave you a homework to try to show that this red part is a non-negative one. Okay, so this is a homework for you. Now, let's take a look at the second comment. So the second one is that the model function with respect to tau is a decreasing function. Okay, to show the decreasing function, we also use the prime or the gradient. Okay, so if we can show the gradient of m with respect to tau is non-positive, then we have shown the result. Now let's take a look at this one. And we still replace this tau with 1 plus alpha, and we take alpha between 0 and 1. So we define a new function h hat about alpha like this. And we do the expansion about h alpha, and we take the prime about h alpha. Okay? Because h alpha is already a quadratic function, and we directly take the gradient, then we get the following result, okay? Which is about PB and PU, as well as some term about alpha. So if we notice that B here is positive definite matrix, and for any positive definite matrix, this term here is actually a non-negative one. So with the fact that alpha is between 0 and 1, so this second term is smaller than or equal to the term that alpha replaced by 1, okay? So after that, we then enlarge our condition by this term, and we put the PB minus PU, this term out, then we do a summation about the left part. And now, after simple calculation, we can see that this term is actually 0. By this way, we actually show that the gradient of h hat alpha is also non-positive one. In other words, h prime alpha is smaller than or equal to 0. Therefore, the original model function with respect to alpha is a decreasing function. This gives our result. With the two properties mentioned above, then we can now solve the dogleg method. Okay, so the dogleg method, actually we solve this model function related to tau, and we already know the properties about m tau. Okay, so how do we solve this model function? We can check the following properties, actually, okay? So the path p tilde tau actually intersects the boundary, okay? So it is actually the intersection between the truss region boundary with the path, dogleg path, okay? So we need to check whether the PB reached the boundary or not. If the full Newton step is already inside of the truss region step, then the optimal solution will be exactly the full Newton step. Otherwise, it means that the p tau tilde will be exactly reach the boundary. Okay? It means that we can directly solve the line segment to intersect with the truss region radius. So we solve this equation with respect to tau is actually a quadratic equation, and we can find the root of this equation, which will give us the solution of tau. Okay? However, do remember that the tau will lie between 0 and 2. It cannot lie outside of this region, okay? Now, as for the choice of the second order matrix BK, we have some comment. So the first choice of BK is that we can use the Hessian matrix at the current iteration. So if this Hessian matrix is available and is positive definite, then we can, of course, replace this BK by the Hessian matrix. Otherwise, we need some choice, okay? We may approximate the Hessian matrix on our own. For example, we use some trust region strategy, or we use some quasi-Newton method to estimate this BK, or we use some part information of the Hessian matrix, okay? So in this case, BK can be defined as the modified Hessian matrix, all right? So it's kind of modification because we cannot know all the information of Hessian matrix. Now, let's take a look at the two-dimensional subspace minimization technique. As the name mentioned here, that we can see that they are actually two-dimensional in the subspace method. So assume that BK is positive definite, and we try to solve the model function like this, which is as usual as before. However, the constraint changes a little bit, okay? So besides the trust region constraint, we also require that P lies in the subspace spanned by the gradient G as well as the Newton step B minus G, okay? So in this case, the two subspace dimensional case comes from here, okay? So P is actually a linear combination of the gradient direction as well as the Newton's direction, all right? So you may think about the dogleg method. So as we mentioned before, the dogleg method is actually two line segment, okay? The first line is along the steepest descent direction, and the second line is actually moving from the steepest descent direction to the full Newton's direction. So it is actually a special case about the subspace method, okay? It's a linear combination of the two directions. However, it is a specified combination. And however, here in two-dimensional subspace minimization, we allow more freedom to the coefficient of the two directions. So we require that P is just the combination of the two parts. There is no restrictions on the coefficient. So it will allow us even more smaller optimization values than dogleg method. Okay, so if we compare the two-dimensional subspace minimization method with the dogleg method, then the two-dimensional subspace method will definitely return a smaller model function value than the dogleg method. And this is a crucial property when we try to prove the convergence result for trust region methods. Okay, we also have some remarks about the two-dimensional subspace minimization. Firstly, this subproblem, we have inexpensive computational cost because it only involves two directions and it is a two-dimensional subspace method. And the result or the subproblem can be reduced to roots of fourth-degree equations, okay? So recall that for dogleg method, it actually reduces to roots of a fourth-order equation. And by the relations of dogleg method with the subspace method, we can guarantee the global convergence for the two minimization methods. Finally, it is actually the extension of the dogleg method, as I just mentioned. And finally, a very special feature for this two-dimensional subspace minimization is that it is particularly probable for the case that B is not positive definite. Okay, so it is probably used in some case where the Hessian matrix is not positive definite. It is very useful in that case. Now, let's make a brief summary about this part. We have introduced the dogleg method, how to solve it, as well as the two-dimensional subspace minimization method. Okay, so in the next part, we will introduce the convergence of trust region method. So we stop here and see you next time.